This video is for those of you who want some additional practice with asymptotic notation, and we're going to go through 3 additional optional examples. Let's start with the first one. So the point of this first example is to show how to formally prove that one function is big O of another. So the function that I want to work with is 2 raised to the n plus 10. Okay, so it's the 2 to the n function that you're all familiar with, but I'm going to shift it by 10. And the claim is that this function is big O of 2 to the n. So without the 10. So how would one prove such a claim? Well, let's go back to the definition of what it means for one function to be big O of another. What we have to prove is we need to show that there exist 2 constants such that for all sufficiently large n, meaning n bigger than n naught, our left-hand side, so the function 2 to the n plus 10, is bounded above by the constant multiple c times the function on the right-hand side, 2 to the n. Right? So for all sufficiently large n, the function is bounded above by a constant multiple of 2 to the n. So unlike the first basic example where I just pulled the 2 constants out of a hat, let's actually start the proof and see how you'd reverse engineer the suitable choice of these 2 constants. So what a proof would look like, it would start with 2 to the n plus 10 on the left-hand side, and then there'd be a chain of inequalities terminating in this c times 2 to the n. So let's just go ahead and start such a proof and see what we might do. So if we start with 2 to the n plus 10 on the left-hand side, what would our first step look like? Well, this 10 is really annoying, so it makes sense to separate it out. So you could write 2 to the n plus 10 as the product of 2 terms, 2 to the 10 and then the 2 to the n, also known as just 1024 times 2 to the n. And now we're looking in really good shape. So if you look at where we are so far and where we want to get to, it seems like we should be choosing our constant c to be 1024. So if we choose c to be 1024, and we don't have to be clever with n naught, we can just set that equal to 1, then indeed star holds, so the desired inequality. And remember, to prove that one function is big O of another, all you got to do is come up with one pair of constants that works. And we've just reverse engineered it, just choosing the constant c to be 1024 and n naught to be 1 works. So this proves that 2 to the n plus 10 is big O of 2 to the n. Next, let's turn to another non-example of a function which is not big O of another. And so this will look superficially similar to the previous one. Instead of adding 10 in the exponent of the function 2 to the n, I'm going to multiply by 10 in the exponent. And the claim is if you multiply by 10 in the exponent, then this is not the same asymptotically as 2 to the n. So once again, usually the way you prove that one thing is not big O of another is by contradiction. So we're going to assume the contrary, that 2 to the 10n is in fact big O of 2 to the n. What would it mean if that were true? Well, by the definition of big O notation, that would mean there are constants c and n naught, so that for all large n, 2 to the 10n is bounded above by c times 2 to the n. So to complete the proof, what we have to do is go from this assumption and derive something which is obviously false, but that's easy to do just by canceling this 2 to the n term from both sides. So if we divide both sides by 2 to the n, which is a positive number since n is positive, what we find would be a logical consequence of our assumption would be that 2 raised to the 9n is bounded above by some fixed constant c for all n at least n naught. But this inequality, of course, is certainly false. The right-hand side is some fixed constant independent of n. The left-hand side is going to infinity as n grows large, so there's no way that this inequality holds for arbitrarily large n. So that concludes the proof by contradiction. This means our assumption was not the case, and indeed it is not the case that 2 to the 10n is big O of 2 to the n. So our third and final example is a little bit more complicated than the first two. It'll give us some practice using theta notation. Recall that while big O is analogous to saying one function is less than or equal to another, theta notation is in the spirit of saying one function is equal asymptotically to another. So here's going to be the formal claim we're going to prove. For every pair of functions, f and g, both of these functions are defined on the positive integers, the claim is that it doesn't matter, up to a constant factors, whether we take the pointwise maximum of the 2 functions or whether we take the pointwise sum of the 2 functions. So let me make sure it's clear that you know what I mean by the pointwise maximum, by max f and g. So if we look at the 2 functions, both functions of n, maybe we have f being this green function here, and we have g equal to this red function. Then by the pointwise maximum, max fg, I just mean the upper envelope of these 2 functions. So that's going to be this blue function. So let's now turn to the proof of this claim, that the pointwise maximum of two functions is theta of the sum of the two functions. So let's recall what theta means formally. What it means is that the function on the left can be sandwiched between constant multiples of the function on the right. So we need to exhibit both the usual and not, but also two constants, a small one c1 and a big one c2, so that the pointwise maximum of f and g, whatever they may be, is wedged in between c1 and c2 times f of n plus g of n, respectively. So to see where these constants c1 and cn are going to come from, let's observe the following inequalities. So no matter what n is, any positive integer n, we have the following. Suppose we take the larger of f of n and g of n. And remember, now we've fixed the value of n is just some integer, like 23. And now f of n and g of n are themselves just numbers, maybe they're 57 and 74 or whatever. And if you take the larger of f of n and g of n, that's certainly no more than the sum of f of n plus g of n. Now I'm using in this inequality that f and g are positive, and that's something I've been assuming throughout the course so far. Here I want to be explicit about it. We're assuming that f and g cannot output negative numbers. Whatever integer you feed in, you get out something positive. Now the functions we care about are things like the running time of algorithms, so there's really no reason for us to pollute our thinking with negative numbers. So we're just going to always be assuming in this class positive numbers, and I'm actually using it here. The right-hand side is the sum of two things is bigger than just either one of the constituent summands. Secondly, if we double the larger of f of n and g of n, well then that's going to exceed the sum of f of n plus g of n, right? Because on the right-hand side we have a big number plus a small number, and on the left-hand side we have two copies of the big number. So that's going to be something larger. Now it's going to be convenient, it's going to be more obvious what's going on if I divide both of these sides by 2, so that the maximum of f of n and g of n is at least half of f of n plus g of n. That is, it's at least half of the average. And now we're pretty much home free, right? So what does this say? This says that for every possible n, the maximum is wedged between suitable multiples of the sum. So 1/2 f of n plus g of n is a lower bound on the maximum. This is just the second inequality that we derived. And by the first inequality, that's bounded above by once times the sum. And this holds no matter what n is, any n at least 1. And this is exactly what it means to prove that one function is theta of another. We've shown that for all n, not just for n sufficiently large, but in fact for all n, the pointwise maximum of f and g is wedged between suitable constant multiples of their sum. And again, just to be explicit, the certifying choices of constants are n naught equals 1, the smaller constant is 1/2, and the bigger constant equals 1. And that completes the proof.